Right, good morning. Welcome to today's webinar. The title of Your First Steps with Flow Simulations. So, I'm your today instructor, William. Okay, so basically it will be a 1 hour webinar. First of all, I would like to credit these slides to build this things from the source system. All right, so this webinar is basically an introduction to flow simulations together with case studies. Right, we will go through a process from zeros until the end of the flow simulations cases. Okay, I will go through the basic steps of setting up a flow simulations studies, and the examples here includes the flows and also the heat conductivities in the solids. So do not worry if you have different cases, because the basics principles or the basics idea of setting up the flow simulations is basically similar. So this is the examples that we are going to use. It's electronic enclosures built by SolidWorks. It's an electronic box with all the electronics components. Okay, and our concern here is the heat dissipated from each component and the heat flows in the electronics box. We will not want it to get overheated. If it is overheated, what are the things that we can do to reduce the heat? So I separate it into 14 subtitles, which includes the pre-processing, the actual analysis, the actual studies analysis, and post-processing of the flow analysis results. So the first one will be preparing the models, creating some flow simulations, specifying the fans, specifying boundary conditions, specifying heat source, creating solid materials, specifying solid materials, and specifying goals, and check whether your geometrical resolutions, whether you need additional things for better results. And then we will go to the studies to run the calculations and build the goals, and everything after that will be on the post-processing. So first of all, we are going to prepare the models. Of course, when you are, for fabrication purposes, we need all the details to be in our assemblies or our parts. So a good practice is to check the models. If there are any complicated geometries, we can simplify it, or if it is not important, we can exclude it from our flow analysis. So this will help in reducing the computer resource and the computations time. So in our case, we will assign a boundary conditions for our fan instead of considering the whole fans model. Because the fans have a very complex models, of course it will affect the machines and it will affect the computation time. So, and another thing is anything which is outside the enclosures or outside the studies boundaries, we will exclude that from our studies. Okay, those are some of the tips for flow simulations. So we are still in the preparing models. So as you can see here, in the design trees, the fan 412s and all the screws are being suppressed or excluded from the studies. So of course, if you suppress that, it will left a holes in your enclosures. So what we do is we create a lid to replace those suppressed components, so that to make sure that it is enclosures, it is still in an enclosure situations. Lids is simply profiles which extrude that cover the holes. Okay, put it this way. So then the second one will be creating the flow simulations project. So normally what we always do is go to the drop downs of flow simulations, go to projects and go to wizards. So you can start up your projects, you can start up your analysis with a new, with just clicking on the new. But it is always a good practice. Even the experts of flow simulations analysis will use wizards because it guides you step by step to your analysis. So it's basically a very good thing, a very good practice to start with the wizard. So the first steps of the wizards will prompt you to key in your project name. So, and also choosing your configurations that requires which configurations that you want to use, and key in your project name. So the second one will be selecting units for your analysis. So predefined, we have all these unit systems. We have all these unit systems. But of course, if you would like to create a new unit systems of your own standards, you can always create it yourself here and then assign it accordingly. So still in the creating flow simulation project, so in the wizards, we can select whether it is an internal analysis or an external analysis. So and then check the heat conductions in solids, because we would like to consider also the heat dissipated from the solid itself, or the heat transfer between solid component. Okay, each of the components we generated heats here, and the heat will be dissipated to the surroundings and also between solids. And then choosing the default fluid, in our case, will be the air. Okay, if you are doing an aircon, there are selections of refrigerants here. So by default, and then select the default solids. Okay, in our case, we will select the steel stainless steels of 321. Choosing the default standard materials will simply means that all the solids component will be assigned with the stainless steel 321. But however, if you would like to define or even assign different materials to each of the components, we can do it later in the project or in the settings. So, and then we would like to put in a heat coefficients. So in our case, we put in the heat transfer coefficients and the initial temperatures of the fluids that we assign, which is air in our case. So a little bit explanations here. Don't worry, you can download this from our website later, so that you can run through that. So then when you are done, just press next, and then we can assign, again, we need to assign the initial boundary conditions for our fluids and the solid temperatures. Okay, we assign with 10 degrees Celsius. So, and then the last one will be the resolutions, which to be simple, this is actually the meshing. So I will talk about that later in another titles. So at the moment, we just set it as default and then finish the setting. So remember that I said I said that the fans geometry will affect the computation time. So we basically already suppressed it earlier. So now since we need a fan, the fan is one of the considerations. A fan is the boundary conditions for our flow studies. We will specify the fans according to the boundary conditions. So fans is one of the boundary conditions for the flows analysis. So we can define it on the surface of the leads. Okay, a surface of enclosures within enclosures. So it can be a split lines, or it can be a solid models, which is a simple cylindrical extrude. So in our case, we have 3 types of fans to be chosen: an external inlet fans, external outlet fans, or an internal fans. So selecting the phase and then selecting the models, that have in the predefined. So if you would like to assign your own fans, if you have enough information, you can always create a new fans with your own name, and then just select from the user defines tab. So, and once we assign the boundary conditions of the fans, so we proceed with others boundary conditions. So boundary conditions basically we can set as the pressures, the mass flow rates of the air, the volume flow rates or the velocities of the wind. Okay, so and then once we have, we will proceed to an actual case of assigning boundary condition here. So we select the inner face of the leads, okay, of the models where the air flows out. Okay, so we assign those face with pressure openings and environmental pressure with environmental pressures. Okay, and then next we would, and then the next thing will be assigning the heat source. So heat source can be assigned with different parameters. Okay, we can have a heat generation rate, volume generations, surface generations, and the temperatures, initial temperatures of the models. So for the first one, for the main chip, okay, for the main chip, we will assign it as with 5 watts. Okay, we're constantly generating 5 watts of heat, and we can rename it as main chip for our future reference. So the next will be a volume source. Okay, again, insert a volume source and click on the 3 capacitors from the design tree drop down, and we assign that with a constant temperatures of 38 degrees Celsius. So, and again, repeating the same steps, name it as capacitors for our reference. So for these capacitors, we does not assign it as a heat generation. We assign it with a temperatures value. So, and then we proceed with the same procedures to PCBs and the power supply. So the volume, this is the conditions. PCBs is a volume source with heat generations of 4 watts. Okay, the power supplies is a volume source with temperatures of 49. Okay, as for the middle ones is a surface generations rate. Okay, so for example, a monitor screen, we can consider that as a surface generation heat, okay, instead of a volume source. Okay, so same thing here. We are going to rename it with the PCBs, small chips, and the power supply, and for our own reference. So next is assigning materials to each of the components. Remember that we assign a default solids to all the components. So in this case, there are certain components with different materials. So we need to assign it individually for correct flow analysis. So there are maybe in the materials database, in the engineering database of flows materials, there are some materials which is not your materials of selections, or which is something that is not in the special materials, which is not in the database. So you can always assign it, okay, by giving a name. Okay, you can add comment if you want, and density, the specific heat, the conductivity types, with the parameters and with the characteristics of the materials. You have it and you can create it. And all of this, it will drop into a columns, into a rows named user defined, so that for us to assign it later. So once you have done creating the solids, and then you will need to assign it to each of the components, which is not stainless steel 3-to-1. So in this case, the leads will be insulators, the heat sinks will be an aluminum, and the small chips will be a user defined of components which we created earlier in this slide. Okay, 2 components, two materials that we created individually, and the main chips is also our user defined material. So once we have a solid materials, we have assigning as a solid materials, then we proceed to specifying the goal of the studies. So goals in importance, where we assign we assign a boundaries, we assign a criteria for the studies to converge. Okay, in certain case, it will converge regardless in every case it will converge regardless what are the goals that you assign to. But however, if you assign a clear goals to the studies, it will converge it will converge faster. It will not take out too much of the computation time. So in this case, we will assign a volume goal of maximum temperatures to each of the chips. Okay, so for the small chips, the PCBs, we will assign with a maximum temperature. It will converge once the maximum temperature is reached. Same goes to the main chips. So these two criteria, these two goals will contribute to the convergence of the flows analysis. So the next, we assign surface goal for the inlet and outlet for the fans and the outlet. Okay, for the inlet fans, we assign an average static pressures. Okay, once it reaches an average value, it will converge. Same goes to the outlet, where the conditions, the mass flow rates reach an average value. Okay, the mass flow rate reach an average maximum values, so it will converge. So once we assign all the volume goals and surface goals, additionally we assign another static pressures of the whole models. So when the average temperatures of the boundary, of the enclosures, when you reach a static average static pressures, it will converge. And also for the temperature flux, when you reach an average value, it will converge. So as you can see here, when you assign the goals with the symbols of a flex and the name GG, it simply means that it is a global goal. If you see a SG with a symbol like that, with an icon like that, it simply means a surface goal. Same goes to VG, which is a volume goal. So next, again, remember earlier we assign as a default resolutions. So of course we can always tune it to the fineness for more accurate results. But tuning it to fineness simply means that it will match everything. With the fineness settings, and results in very long computation time. You will get accurate result, but it might take very long to finish up your study. So in this case, we will measure the smallest gap we have, which is at the heatsink of 0.1 inch. So we assign a minimum gap size to it, so that it will automatically measures smaller when it detects gaps of 0.1. Okay. So this is particularly useful when you don't have a powerful really powerful computers, which but you would still like to have a more accurate result. Okay, the geometrical resolutions will help a lot here. So the next thing will be simply running it. Okay, we can check. If you do not want to solve it first, you want to check on the meshes first. You can always check on the meshes without checking on the solve and run. First, it will run the mesh. If the mesh, you can check on the mesh. If the mesh is satisfied, then we can proceed with the solving. Then the next will be on viewing the results. Will be on the post-processing of our studies. So first of all, we would like to check on the goal or the goal plot. Okay, you will have you can view the goal plot. Okay, checking on each of it, and click on show. It will came out a tables which includes all the value, the average value, minimum value, and maximum value. 100% simply means that it is already converged in our case. Okay, so once you're done with this, and you can export it into Excel, and for the first sheet, it will give a summaries of all the studies, and the continuous sheets, it will give a detailed values of how it converges. You will have a graph, and you will have the task from each iteration. So, and once we've done reviewing the results, we would like to know the flow trajectories of the air from the fans to the outlet. So we can call it out, okay, and selecting the fans and fine-tune the settings to see your flow trajectories. And this is an example with that particular settings of the electronic box. Okay, we can see the flow trajectories here. Okay, I will view again. So from the fans, the flows come out from the fans to the outlet, flowing through each of the component. Okay, if we see clearly here, so we'll know that the flows passes through the heat sinks a lot. It passes through others component too, but however, at the second rows of the PCBs, the second rows of the small chips, the flow is not the flow trajectory test is relatively lower, relatively less compared to others portions of the enclosures. So we might have a problem here where the heat does not dissipate, where the heat is not carried away by the flow. So design changes will need to be done here. It's either on the arrangement of your PCB components or the positions of the fans. Okay, it depends on you. So we can do optimizations once we got the results, the flow analysis result. However, I will not talk much on that. Okay, that will be another topic. So what I focus here is on pre-processing studies and post-processing of our results. So next, we can check on a cut view, a section view, I would say, a section view of the enclosures. Okay, cut to a sections where you can see the velocities of the airflow. Okay, so we will see that the weight portion simply means that velocity is high. So we can see it more clear. We can see it clearer here, where the velocity is higher on these particular portions on the outlets, without flowing to the second rows of the PCB, the second rows of the small chips. So it's obvious that we need to do some design changes. We need to optimize our models, either moving the fans or changing the positions, the locations, or the components locations. Okay, so we would like to know on the fluid temperatures cut plots too. We would like to know on the solid temperature cut plots too. So as for the fluid temperature cut plots, you can see here, it's logical here where you see if the flows of the velocity is high, the temperature will result in lower temperature. Where if the flows does not flows through there, or the velocities of the fluid flows, the air flows is slow, the temperatures is higher at this portion. Okay, so this will be the air temperature. So we would like to consider also the temperatures of each of the components, the sections cut plots of each component's temperature. Okay, we can also check on that too. Okay, where the wall, what is the temperature of the wall, what is the temperatures of the heat sinks, the capacitors, the power supplies, and also the PCBs. Okay, from here we get the results and we can do optimizations of what are the components that we need to pay attention to. Okay, so if of these give a very high temperatures, or if that is acceptable temperatures, we can leave it, or else there are changes that we need to do. And of course, beside the section view, beside the cut plots, we would like to know the surface plot too. Okay, the surface plot simply means that we can select on the component, the surface of the components, and check what are the temperatures on each of the surface. Okay, we'll see, and then we can look into what are the portions that we would like to pay attention to, or if you encounter a thermal warpage situations, surface plots will be a good post-processing features for you to check on the components of where are the possible positions where the thermal warpage will happen. Alright, so I believe that will be my last slide. Alright, yep, that's my last slide. So I will point an end. Okay, so thank you for your attention. So if you have any questions regarding the flows, you can always email me. This is my emails, and this will be my contact number. Or you can always call our office for support. If you'd like to know more on this, you can always go to your office and do a simple demo on your particular industry. Okay. As for the slides, we will upload our slides in our website. Okay. After this, and we will also upload articles regarding these topics in our blogspot. So do stay tuned with us. So thank you for your attention, and see you again next time.